Welcome back. Today we're going to take a look at the Fibonacci pattern again. This will be part 2, and we're going to take this pattern that we created in geometry nodes. But I want to do something more interesting today because last time we pretty much got the basics of this Fibonacci pattern that uses the golden ratio for the angle to distribute points. And the golden ratio is something that's derived from the Fibonacci sequence. But you can watch part 1 if you want to know more about that. But what we did was pretty much distribute these points in 2D only. We didn't use the z-axis. We only, at the end, we added a little bit of noise that might move the points in the z direction. But the pattern itself is 2D. And we are in Blender 3D. So I wanted to do something more 3D with this pattern. So today, we're going to take this pattern and distribute the points on a sphere. Instead of on a flat plane. So let's go into Blender, and this is where we left off in part 1. As you can see, a flat-ish plane. If we remove the noise there, then you can see this is a flat pattern that is pretty cool, and it looks quite complicated. It adds these points and it creates this cool flat kind of pancake. It's nice, but now I want to take this and turn it into a sphere. And that has a bunch of challenges, but first I wanted just to visualize how simple this pattern actually is by just making one of these points red and following the trajectory of one of the points to show that they just move in a straight line. And another thing I like to control is this noise. I would like to control that in the modifier settings. So let's take a group input, and first we escape it from this frame by using Alt-P and then adding it here where, maybe there, where I want to control this scale, and I want to call it, instead of scale, I would like to call it the noise strength. Make sure you spell that right. Okay. Noise strength should go from 0 to something huge. And for a default, yeah, this is fine. Okay, so now we can control the noise over here. Oh, we disabled it. There we go. Okay, so now we can control the noise amount over here, and you can see that it just moves a little bit randomly this way. Pretty cool, but we can turn it off if it's getting distracting. So this pattern is really simple. All we do, if you remember from part 1, is we calculate an angle for every point. So we choose an angle and we stick with that angle. And then we calculate the distance, how far does it move out from the origin. And it pretty much just moves in a straight line. Even though this looks really complex, it moves in a straight line. And to visualize that better, it would be cool to just create make one of these points red. So if we want to do that, there is a little bit of a challenge there, because you could say, okay, let's set the material, and we can use a selection. So we can set the material on a subset of our instances, and let's create a material. Currently we have this gray material, that's the default. We can add like a red material, and we make that red and copy that color, and then we also make it red in our viewport. All right. Cool, and we can remove this. Now we can choose it here, and now everything becomes red, of course. But if we could say, it will make sense to use the index, right? So we can get an index and then we can compare that index if it is maybe greater than. So if it's greater than 0, then we want to select this. That should be everything. Yeah, that's still everything because the index is always greater than 0. Unless it's 0, maybe. But that doesn't really do anything. So if we increase this, what we see is that we're not working with the index of the instances, but we're working on the index of the mesh vertices. And I think the reason for this, I'm not totally sure, but the reason for this, I think, is that we are using a set material node, which has the domain of the points of a mesh. That's the reason. Because we could, we could do other nodes where we select something and then sometimes it uses the instance index. So I'm not sure what the most elegant way is to do this, but what I came up with is setting the material on some of this, then joining that with the originals and then just removing part of them. So, okay, let's just build this out instead of talking about it. I'm gonna remove, delete geometry. Yeah, it's called delete geometry. I want to delete geometry here as well as here. And I only want to delete the selection. And then I want to delete the inverse of that. So not where this selection, we pretty much invert the selection with this not node. And that's what we plug in here. And then the opposite is being removed there. And here we can choose the domain. So now we are on the point domain, the same as the material. And then we can remove that selection. So here we want to just delete a bunch of points. And then the points that are left, we want to make them red. And then join them back together. So now we don't want to be on the point domain, but on the instance domain instead. On both the delete. So now we're working with the instances. So this is a pretty cool effect. And we can just create this. But if we want to make one point red, we can say if this is equal to, and let's say we take number 3. This is point number 3. If we go all the way to the beginning when there's only 3 points, we can see that. So this is index 0, this is index 1, 2, and then 3. That's the red one, and the only reason I wanted to do this might be a useful thing to know how to do. If there's a better way to do this, please leave a comment, because I don't think this is the most elegant way of making one point red with all these nodes. But anyway, now we can clearly see that, especially if we remove the noise, we can clearly see that we start from the origin, we pick an angle, and we keep moving in that angle in a straight line. So that is what this pattern does, and it looks really complicated, but all it does is moves points in a straight line, picks an angle for every point, a different angle, and that angle is based on the golden ratio. That's why this pattern looks so cool. But then it just moves it in a straight line. So to make this move on a sphere, instead of in a straight line, we want to move it on an arc. So instead of this, am I drawing? Yeah. Okay, let's create a new one. So instead of moving on a straight line like we do now, in a certain like travel distance, instead, we want to pick a radius, r, and we move around that midpoint, like this. And then here we still have the same radius. And then we are working with this angle we are working with an angle over here as well to pick which direction we go into. But then here we have another angle. So this first angle, I think I called it alpha. So let's call the second one beta. So this angle beta is something we need. And when we know this, we can already calculate how far down we need to move in the z direction. Because currently, with this 2D pattern, the reason it's 2D is that we only do something with the x and y. We don't do anything with the z. So we can move the entire stack of points up and down like this. But to make it more interesting, we can calculate for every point the proper z location based on this, how far down we need to go. And we can calculate that with the radius and beta. So the angle beta is just the travel distance divided by the radius. And then the amount of z we need to move down is the sine. Yeah, I think it's the sine of the of beta times r. So it's r times sine of beta. And this is very similar stuff to what we did, where we calculated the angle and the distance, and then we did the cosine and the sine to get x and y. We have to do something very similar from this view, because all of this stuff was from the top view. And now we're from the side view calculating this, and that allows us to get the z, how much we need to move down. So let's calculate beta based on this distance that we have here. So I can actually reroute this and we can just label all of these things. This is our travel distance. And then we want to calculate our angle beta, which is a division. So let's divide. And we divide by the radius, but the radius is something we don't have yet. We do have a radius actually, but that's the point radius. So let's rename that the point radius, because that's like the size of all our points. So I want to expose this radius as well that we need there. So let's do that like this. And that will be our sphere radius. And let's see. That is a very important setting. So I want to move that up here. And this radius is our point radius. Let's make that really clear. And then we have spacing. Maybe spacing is more important than the point radius. Okay, and the sphere radius can be from 0 to infinite, pretty much. Default, let's do 10. And it's a distance. Okay. Let's set that to 10. And now we are dividing our travel distance by the sphere radius. So that gives us the beta angle. And we can plug a sine in there. And that will give us how much z we need to go down after we multiply with the radius again. So we take that radius again, we multiply by that. And that should go into the z. All right. Pretty cool. I'm not sure if I did something wrong here. It should be the cosine probably. Yeah. Okay, so we start off a cosine kind of, if this is 0, a cosine kind of starts like this and a sine starts like this. And a sine goes like this and a cosine goes like this. So cosine starts off very slowly going down, 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 and then it starts to speed up. And that's pretty much what we need here. So I was just, yeah, that was just my mistake. This should be cosine. I don't know, do you have like a eraser? Oh, cool. Yeah, so this should be cosine instead. All right, that makes more sense. Okay, and then we get a sort of a spherical pattern in the beginning, but then it kind of moves out and it starts to become like a sine wave pattern. Reason for that is that we are properly calculating our z, but we're not properly calculating our x and y, because the x and y is still based on the travel distance. But instead of travel distance, we should plug something else in. So, I don't know if this is readable right now. So instead of travel distance, we need to calculate the horizontal distance. That's like this. Oh, this is kind of annoying that it's like thinking I try to make an animation. Maybe if we lock it. Okay, so this horizontal distance is a little bit less than the travel distance, because the travel distance travels across along the sphere. So how much in the horizontal is gonna be less, and that is actually, so the horizontal distance, that is actually equal to r times the sine of beta. And that's a very common pattern you see if you calculate something like this, going from an angle and a radius. You take the angle and take the cosine and the sine of the angle and multiply it with the radius. That's the same thing we did here from the top view in x and y. Now we're doing it kind of in z and outward in the xy plane. Same pattern, going from an angle and a radius to coordinates. So we can copy this, and we need more space. We can copy this cosine and multiply, duplicate it. We plug in the same beta angle, and we might want to just label that to be beta, our beta angle. And we plug that into the cosine. That should be a sine in this case. And we multiply that with the radius of the sphere. And this is our horizontal distance. So instead of plugging in the travel distance in x and y, which just goes out infinitely, the horizontal distance goes out and then back in, because we move over the sphere. So I'm gonna add another one, and it automatically names that. That's interesting. Let's call this the horizontal distance. And that's what we get here. So if you plug that in, now we should get a sphere. Yeah, that looks like a sphere. Cool. And as you can see, the points move over this sphere with a radius of 10, and we can change this radius, and that changes, and we can change the spacing. And you can see the problem we're having now. We're moving properly over a sphere. We're distributing the points on the sphere, but the distribution is not very consistent. So in the beginning, they are spaced with a bunch of space in between, and then they get closer and closer together. The reason for that is this is our second kind of challenge. The first challenge, we're done. We calculated the z and the x and y properly, but now we just have to change our travel distance and the rate that the travel distance changes. And that is that is our next one. So the last time, to fix our distribution problem, because we also had a distribution problem in the first part with the flat pattern, the way we fixed that was using a square root, and I'll try to explain why that works. So if we have like what we pretty much want to do is we want to think about the area that each point takes up. Because if every point takes up a consistent amount of area on our pattern, the distribution will be really consistent. But what we do if we just plug in this thing straight, we're having a constant travel distance. And then the area is not constant, because the area as a function of travel distance looks something like this in the flat case. And we want to make the area increase consistent. And then we want to calculate what is the travel distance going to be if our area increases in a consistent rate. And that's pretty much the inverse of this. So here we want to know what is our distance. What distance do we need if our area is going to increase at a constant rate? And that is pretty much the inverse of this x squared pattern. It's going to be the square root of x. And it's going to be proportional to that. And that's why adding the square root worked for our flat case. But now with the sphere, it's slightly more complicated. So with the sphere, the way that the area increases, it's pretty much, if you have this sphere, you move this distance, the area is proportional to this kind of radius, and I should probably not call this radius, but this horizontal distance that starts off small, it gets bigger, it gets to a maximum, and then it starts to get smaller again. That is pretty much proportional to the area that the points are taking up. So over here, the area will be the space between the points will be bigger, and here it will be smaller if we increase this distance with a constant rate. So let's try that. If we remove this square root, the distance between the points in the beginning should be very packed. Then it should go out very wide. Then it should get packed again. And that's what we see, because that space, which is the area, is proportional to this distance. So how does this distance change over the course of the travel distance? That is the area and the travel distance. That looks, in the beginning it looks similar. So it starts off like this, like the square, but then it goes back and it slows down again. And this is pretty much a cosine of x, and it's shifted a little bit, but it's proportional to that. And so in order to distribute the points properly, we have to inverse this. And there is a function called the arc cosine, which is the inverse of that. So we have to get something that looks in the beginning similar to the square root, and then it goes like this, and it kind of mirrors what we do here. And this is the arc cosine of x, or the cosine -1. That's another notation. So that then we get something like the travel distance or angle, which might make more sense, and based on a constant increase of area. And this top point should end at pi, because at pi we are rotated all the way from the top to the bottom. That's half a rotation, that's pi radians. So this should go from 0 to pi in this kind of shape. And let's open a graphing tool that might be useful to visualize this. So in the flat case, the area increase for the flat case is pretty much x squared, and that gives you this parabola. So the opposite of that is what we want to get is the distance in the flat case is equal to the square root of x. And that's pretty much the mirror across this line x equals y, it mirrors across that. And that's pretty much giving you the inverse. So what we get with the spherical case, so that's like the area for the sphere increases something like cosine of x. And it should start, of course, at 0. And then it goes up and then it slows down. So maybe it should be the inverse of that, the negative cosine. And then we move it up by 1. So let's add 1 to this. And that gives us this. This is how the area increases. So in the beginning, it goes very slow. That's why it's very packed in the beginning. Very closely packed together. And then in the middle, it starts to go really fast because this slope is fast. And then it slows down again. So that's what we see. So if we want to reverse that, we want to inverse that, we do something like we want to calculate the angle for the sphere, which is it's proportional to the travel distance, which is the arc cosine of x. And that's a very weird looking graph. Let's turn these two off. That looks like this, and so we have to shift this around a little bit. So we here did 1 minus the cosine of x. So if we take 1 minus x and plug that in over here, we pretty much get what we need. So here we get something that goes from 0 to pi, and it starts off fast. So it will push out these spheres very fast. So you get more space over here. Then it slows down. So over here, it's very slow because we have a lot of space. And then it speeds them up again. So the pattern should look like this. The arc cosine of 1 minus x, and x is the travel distance that we, x is how far we want to move the point out. And that is this part. Actually, I'm going to do this after we divide by the radius, because that makes it easier and it lets us work with an angle beta. And the angle, it makes sense that the angle goes from 0 to pi. So over here, I'm going to take this, I'm going to do the minus first, the subtract. So we take 1 and we subtract this value. That is this part. And now we take from that result, we take the arc cosine. So arc cosine, we have a node for that. And that should go into the beta angle because that goes from 0 to pi. And that distributes our points a lot more consistently. And right now the spacing is huge because we just calculated the proportional spacing because we can always change this and multiply this with our spacing. So if we reduce the spacing, we can see we have a very consistent distribution of points, which looks really cool. And if we animate this, this is how they move down. And now we can still see our red point. And instead of moving in a straight line, from the top view, it still moves in a straight kind of line. It's just moving out in the same direction, but it moves in an arc like that across that sphere. And this is what we get. And if we change the radius, everything works, except for the spacing, which if I change the radius, I want to keep the spacing kind of the same. The way to do that is, instead of dividing by the radius, we have to divide by how the radius affects the area. And that's the square root. That's the square of the radius. So we have to take the square of the radius, which you can do with a multiply node. You can also do it with, you can actually do it two ways. You can do it with a power. And you can take it to the second power. And that's gonna change our spacing So we can now increase it again. And now it's very nicely packed together. And if we change the radius, that distance stays kind of the same. So very cool. And the other way we can do this is, I don't know, in my mind, this way using a multiply is faster because it's kind of simpler. We take the radius and we multiply it with the radius, and that pretty much squares it. So instead of that, I'm gonna remove this and plug in this one. In my mind, this is a faster operation. So cool. All right, so I want to move everything inside of there. If that is, I don't know what the easiest way to do that is. Move everything like this. Okay. Because this is all pretty much caring about distance. And then here we're kind of working with an angle. Okay. But yeah, that is how you set this up. And we can change our red point by changing this changing this index. And that's it. Let's hide our nodes. And we got a pretty cool result of our Fibonacci pattern now moving across this sphere. And they kind of look like they disappear over here, but that's just, they're all stuck to the same point. So you could add something that makes them actually disappear, but I'm not going to bother with that. What I want to do instead is move all the way to the end of our animation and then make the sphere such that, or change the radius such that they all cover exactly the sphere. And we can play with the spacing, maybe add a little bit more space, and we can make this bigger to something like that, where they cover the sphere exactly with 1000 points. And that's our final sphere. Looking really cool. And now we can introduce the noise back to make this look a little bit more organic and complex. And that's our animation, starting off really slow and adding these points in a really seemingly random way in the beginning, but now you start to see a pattern and they start to move, and there we got our red point. And they start to cover a sphere. All right, that's it. Thanks for watching. If you're still here, thanks for sticking through all of this. I hope you learned something, and I will see you in the next part.